So if you're new to us, Oasys stands for OV Arup Systems, and we are Arup's in-house software development team, and we provide digital solutions for structural, geotechnical, and geotechnical engineering, as well as for pedestrian simulation. Being a part of Arup as an independent company means that we are focused solely on delivering leading engineering solutions. Now, some general notes before we get going. We will have a question and answer session at the end of the session, and questions you might have, please add them to the Q&A section of Teams, which you can find towards the top right corner of your screen. If you don't see a Q&A option up there, if you just put your questions into the chat, and we will go ahead and move them into the Q&A section and answer them then. So what we'll do then is we will answer the questions at the end. So without any more waiting, we've got two presenters for you today. That's Matthew Brown, our Senior Geotechnical Engineer, and Samila Bandari, Senior Computational Scientist. Matt's going to start, so I will hand over to you now, Matt.
Great, thanks, Andrew. So firstly, thank you to everyone for taking time out of your day and joining us for the latest Gofer webinar. As Andrew said, my name is Matt. I am a Senior Geotechnical Engineer for Arup and have been for the best part of 15 years now. In that time, I've done all sorts of geotechnical design that I'm sure a lot of people on the call will be familiar with, but I think it's important to say that my background is as a practicing geotechnical engineer. I'm not in sales and marketing. I'm not a software developer. That's the sort of position I come from when I talk about Gofer. We've got a lot to cover today, so I recognize a few faces in the chat, but I'm sure there are a few new ones as well. So I'm going to have a bit of a recap or introduction to Gofer, what it is, and why we're developing it. Samila is then going to talk a little bit about the new consolidation solver and some sort of details on that side of things. And she's also going to talk about some of the performance increases that we've realized in the last few weeks. We're then going to hear from some Arup engineers about their real life use of Gofer in their day-to-day projects. I'm going to cover some validation and verification type examples and also give a short introduction to the Gofer user API. So what is Gofer? Gofer is Oasys's general purpose geotechnical finite element analysis tool. Importantly, it's our first piece of cloud software, and we'll talk a lot about cloud and what that means over the course of the webinar. We see cloud and Gofer in particular as the future of our geotechnical software suite, or much of our geotechnical software suite. Gofer looks very different to our conventional geotechnical software. We've spent a lot of time using modern design and development practices to make that the case, make it easy and quick to pick up and to use. In time, the intention is that Gofer will incorporate some of the existing geotechnical desktop software, the sort of plane strain type, Oasys through flexible retaining walls, gravity retaining walls, Greta, and Oasys slope, things like that. The idea is that they will in time be incorporated into Gofer, and that will allow us to retire those desktop software and focus all our attention on Gofer. What we found within Arup is that there are lots of existing finite element analysis tools, but they can often be very time consuming to use. They have a very sharp learning curve. Graduates picking up these software take a long time to get up to speed. We've also found that the licensing can be very expensive with some of these pieces of software. And all those things are fine on some jobs, but on other jobs, they just can't accommodate that cost and time, the program implications of learning those pieces of software. Hence, we've been working on Gofer. So some of our existing geotechnical desktop suite is very quick and easy to use, but in some cases was lacking some of the sophistication in output and calculation methods and so on. For example, using through is very good for flexible retaining walls, but it doesn't give you much information about ground movements away from those walls for things like damage assessment and so on. Hence the need for a easy to use geotechnical finite element program that will give you that level of sophistication without the time penalty in getting up to speed with a very detailed and sophisticated finite element package. The idea with Gofer is that it provides an additional tool with some new benefits. So it's not intended to replace every other tool on the market. It's just an additional tool that we as geotechnical engineers can use in our day-to-day design tasks. We spent a lot of time in Gofer making sure that it's can be set up and run quickly and easily. I talked about the sophistication of the output. There's potential to reduce costs. Gofer is it's a cost-effective solution, cost-effective finite element solution compared to some of the other software on the market. So there's potential for cost savings there. And as I've mentioned, with time, the idea is that it can incorporate some of the other individual bits of software that might have been used historically. And so there's potentially a cost saving, license saving there. It's on a journey, and there's a very enthusiastic development team. And so, you know, it's an exciting project to be a part of. Gofer is different to our other pieces of software and other pieces of software on the market. I've mentioned how we have really spent a lot of time and energy into making it easy to use and easy to learn to use. We have a team of UI UX designers who think through all the features we're putting in and make sure that the interface makes sense, make sure that if you click on a certain button, the thing you expect to appear does appear, and all that thought and effort and time really has paid off. I think the feedback we've had so far from users is that it is easy to pick up and easy to get models running and useful output without that sharp learning curve. Gofer also takes care of things like mesh refinement, so that you can manually refine the mesh, but the auto mesher is designed to give a good mesh in the majority of situations. Things like boundary fixities are automatically applied. You know, you can set up a model in a comparable time to some of the other Oasys Geo desktop suite, but you get the benefit of more sophisticated output than you might not get from some of those other pieces of software. Gofer is a cloud software, so it sits in the cloud. And what I mean by that is that there's nothing to install on your local machine. You just go to the URL, log in, authenticate, and you're there. You have Gofer. You can use the most up-to-date version then and there. What it also means is that the solving of the models is done by a server on the cloud, or the number crunching is done up in the cloud. So suddenly the specification of your laptop doesn't matter anymore, because all it's doing is rendering the web page. And as soon as you realize that, the scope for doing huge quantities of analysis suddenly becomes really feasible, like sensitivity checks, parametric analyses, solving multiple models in parallel suddenly becomes a viable thing to do, because we can make use of very powerful servers in the cloud. It means all users are automatically on the latest version. There's no sort of not using it for a little while and then realizing you're a version or two behind. We're not tied to a conventional release schedule anymore. There's no sort of big annual release. Instead, we can drip feed new features and improvements as we're finished with them, as we're happy with them. We're not tied to that conventional release schedule anymore. Another huge benefit of sitting in the cloud is that the models are hosted in the cloud. You can download a local copy and file it on your server as needed, but when you're working on a model, it's sitting in the cloud. So that means that if I'm collaborating with someone else, if I'm sharing it to another engineer to check or to sort of carry on my modeling, all I need to do is share the URL to them, and they can authenticate with Gofer, click on that URL, and they've got the model there ready to go. There's no sort of downloading and copying, sending gigabytes of data anymore. The final point here is that Gofer is designed from the bottom up to sit within larger sort of automation processes, larger workflows. I'll talk more about the API later on, but the idea is that Gofer is very easy to slot into bigger, more complicated workflows, and as part of that automation can, you know, really start to unlock very exciting analytical capability. In terms of Gofer's capability, it can do, everything is there for a usable piece of geotechnical software. The geotechnical tools that are there, we have linear elastic and more Coulomb soil models. We have drained and undrained behavior, undrained B and undrained C in conventional terminology. Plane strain, automatic meshing. We have a CFI reduction algorithm for geotechnical stability type problems. We have a seepage solver for sophisticated groundwater conditions. We have a consolidation solver, which we're going to hear more about in a little bit. There's all the usual structural tools you'd expect to be there, beam elements, interface elements for sort of soil structure interaction type modeling, props, node links, pin springs, UDLs, point loads, pre-described displacements, everything you'd expect. We've got some nice usability tools in there, so cross sections, sample points. I talked about sharing models as well, really nice feature. And all of this is controllable from the user API. So it's the API is built in from scratch. It's not sort of a bolt-on. In terms of what you could model, anything that you could draw really, flexible retaining walls, sheet piles, contig secant walls, diaphragm walls, cantilevered or propped, installation effects of those walls using interface elements, various forms of ground improvement, slopes, configurations of slopes in and around retaining structures that other software sometimes struggles with. CFI calculations for geotechnical stability, seepage problems, if you're looking at flow through a dam or groundwater flow into an excavation, something like that, loading problems, unloading problems, damage assessment type, ground movements, nearby to things that we might be designing in the ground, buried structures, cut and cover tunnels, anything that you can draw really within the limitations of the software. So that was our introduction. I'm now going to hand over to Samila, who's going to talk in a little bit more detail about the consolidation solver.
Thanks, Matt. I'm Samila. I'm a computational scientist at Arup. I was involved with the developing the solver behind Gofer. I was a geotechnical engineer prior to that, working with Arup for 9 years now. So I'm going to talk about Gofer's new consolidation solver today. We all know that modeling consolidation is a key part in geotechnical FEA analysis. So having this feature will make Gofer a useful day-to-day tool for geotechnical engineers. We use consolidation analysis to dissipate excess pore pressure under applied loads. Say you got some construction stages with undrained loading. This will generate excess pore pressures in the mesh. The consolidation solver lets stresses gradually transfer from the pore water to the soil. As this happens, excess pore water pressure dissipates, causing the soil to deform. This is a fully coupled process, and we have implemented a consolidation solver in Gofer to capture it. Gofer has different options for consolidation. So under the calculation type, there's a new consolidation button. This contains 3 different calculation types, namely the minimum excess pore pressure, degree of consolidation, and a defined end time. When you run a consolidation analysis in Gofer, no changes are permitted to the material, the mesh, or the loads. You need to set them all beforehand and run the consolidation as a self-contained stage. This includes switching the material from undrained to drained, or setting long-term water tables or long-term loads. Now I'm going to show a simple demonstration on how to run a consolidation analysis in Gofer. I have set up a simple excavation geometry that has 10-meter deep excavation with water table. The stages are set in the configure stages tab. The initial stage has only drained material, topsoil is made ground, soil underneath is clay type material. We set 4 undrained stages by switching the clay material from drain to undrained. The undrained material is undrained effective stress type material. This will generate excess pore pressure during excavation. We add the necessary parameters such as effective stress parameters and undrained shear strength. And also in this model, I considered soil structure interfaces. This model has 2 excavation stages, and I'm adding a base slab at the last stage of the construction stage. In the results tab, we can see the results for these construction stages. In the initial stage, the total pore pressures are same as the steady state pore pressures due to the applied groundwater table. And during the excavation, you can see that the pore pressures are changing due to the unloading. Soil is also heaving on the excavation site too. We can also see that the undrained stages generated excess pore pressures. You can also see the generated mesh in the tabs below. So now, if we want to see the long-term response due to the excavation, we need to run a consolidation analysis to dissipate these excess pore pressures. And to add a consolidation stage, we go to configure stages. We first create a new stage where we switch the materials from undrained to drain, as I'm showing here. We also need to add the corresponding permeabilities for these drain materials. Once we set up the permeabilities, we can now create a consolidation stage. So under the calculation type, we pick consolidation and select minimum excess pore pressure option for this model. This will allow the model to fully consolidate. In order to run these stages, we go to results. You can see Gofer has identified the new stages. Then we press analyze. We can also check the stages results while the analysis is running in Gofer. So now you can see the total pore pressures are same as the steady state pore pressures associated with the water table. The excess pore pressures have dissipated and they are less than the minimum excess pore pressures we have assigned. You can also see the stage displacement happen during the consolidation stage. And in the messages section, it shows some useful information such as total consolidation type and prop forces. This is just a simple example to show how we would use the consolidation analysis in Gofer. Next, I will explain why Gofer's consolidation analysis is both accurate and stable. First, why is stability is important? It is because we are dealing with a complex problem. We know that the soil behavior is inherently nonlinear, and in consolidation, we need to solve a coupled system of displacements and pore pressure. To handle this in Gofer, we have implemented the fully implicit nonlinear iteration algorithm. Fully implicit methods handle nonlinearities more robustly by solving iteratively at each time step. This ensures better convergence and accuracy. We adopted an unconditionally stable iterative method. This this allows for larger time steps without the risk of instability. This also gives us a fast solution. Additionally, the current solver is designed to incorporate advanced effective stress-based soil models in the future. This will allow Gofer to expand quickly. Another important factor for stability is maintaining a smooth pore pressure field. Some of you might have noticed that in some software, pressure oscillations can occur during certain undrained construction stages. These oscillations affect accuracy in the undrained phases. This will make it harder to converge during the subsequent consolidation stages. This happens because the classical method calculates pore pressure at integration points, which can lead to discontinuities across the mesh. This behavior can cause pressure instabilities in certain models. This is a commonly stated issue in geotechnical FEA literature, and most software smoothen the pore pressure field for the purpose of presentation. In Gofer, we observed similar issues in our old undrained solver, but we decided to address this issue by replacing the undrained solver with the new consolidation solver. Now we run the undrained stages by running a single time-step consolidation solver using default permeability for undrained materials. We solve both displacement and pore pressures at the nodes iteratively, bringing volumetric strains close to zero. This approach provides a smooth pore pressure distribution across the mesh, and the convergence is greatly improved. Next, I will talk some of the performance improvements we have made in Gofer. We have made some changes to our FEA solver to achieve fast and more accurate solutions. We optimized the iteration algorithm to converge faster with fewer iterations without sacrificing the accuracy. We achieved this by integrating a well-known acceleration scheme into the nonlinear algorithm. This has reduced iteration time by 65 to 75%. Additionally, we adjusted the default iteration parameters, resulting in an extra 5 to 10% reduction in iteration times. We also made a bold choice to replace the old undrained solver with the consolidation solver, as I mentioned in the previous slide. This change has greatly improved accuracy and convergence, putting us ahead of our competitors. The new consolidation solver provides a fast, time-dependent solution thanks to its fully implicit iterative scheme. Apart from the FEA solver, we also made some updates to the C5 reduction algorithm. In this algorithm, we reduce the friction angle and cohesion values over a series of runs until the model fails. This allows us to calculate an implied factor of safety. Previously, we used a bisection method where strength was half at each run. In the example shown here, this method took 10 runs, but 6 of them reached the maximum number of iterations. Now we have implemented the successive reduction method. While it takes more runs, only 2 of them reach the maximum iterations. This makes the overall process faster and more precise near the failure threshold. Our next improvement is increasing the computing power in the cloud. We have doubled the power, which will give users an even greater speed boost. And this is an added benefit of Gofer running in the cloud. And now I will hand over back to Matt.
Thanks, Samira. Really interesting, some clever stuff going on there. So Gofer is used within the Arab geotechnical community, and we are going to hear now from a couple of geotechnical engineers on how they've used Gofer and their thoughts on the software.
I'm Adam Pickles. I'm a senior geotechnical engineer for Arup in Leeds. I've been using Gofer for the past year. I've looked at a range of problems, but I've mainly focused on assessing existing gravity retaining walls, both looking at the effects of changes in loading on the wall and also designing mitigation measures to improve the stability of the wall. From the outset, I was really impressed with the user interface of Gofer. Running software from a web browser is a change from the traditional software we're used to, but I found the process very intuitive, and with a bit of guidance from the online help, it was straightforward to get a model set up. The interface for drawing models is really clear and simple. A big benefit to me was that having set up a model with all the required stages, it's quick to go back and adjust the geometry of soil blocks or to modify a material property and then rerun the analysis. This allowed me to quickly undertake various sensitivity runs to understand the behavior of the walls. Running multiple sensitivity analyses also highlights the benefit of Gofer being based in the cloud. It was possible for me to review other models or get on with some other work without my laptop being tied up processing the ongoing analysis. When it comes to reviewing the results of Gofer analyses, the overall graphical plots of contour and displacement vectors work well. It's also possible to draw section lines that can be used to create plots. However, the actual plotting interface is currently quite limited. I was wanting to compare results from different stages and different models to see the effect of sensitivity analyses I'd been running. I also wanted to process the results and sum up the resultant forces for comparison with simple limit equilibrium calculation results. Whilst I could have copied the results out into a spreadsheet for further processing and plotting, the solution for me was to make use of the API. Using the sample code from the help section, I was able to start interacting with the model and the results from with Python code. Over time, I've been able to build up a library of tools that have allowed me to interact with Gofer, and I'm now able to plot and compare results from multiple model files and analysis stages. Whilst the API does require a bit of knowledge of coding, it presents a range of opportunities for further automation. Overall, I think Gofer is a valuable addition to our analysis toolkit, and I'd encourage engineers who have not yet tried it out to give it a go. Thanks.
Hi, my name is Paddy Simingo Turner. I'm a geotechnical engineer in the Arup Sheffield office. I've used Gofer on several different projects now, predominantly looking at embankments and impacts from them to underlying soft soils or variable actions on embankment. I've found Gofer to be intuitive to understand the basic geometry and material input parameters, and is simple to manipulate this base data. Online resources have helped me develop models and identify errors I've had. I've used Gofer over more traditional software when considering non-standard problems and solutions. The output is clear and easy to visualize. With some of the earlier projects I worked on in Gofer, I compared it with more standard software, such as Plaxis and Oasys PDIS, with the results tying in well.
Really interesting to hear from other engineers who are using Gofer in their day-to-day work. So now I'd like to talk a little bit about benchmarking and validation, how we make sure Gofer is working correctly. Firstly, because it's a very important thing to talk about, and secondly, because I've had a few people ask about this as time's gone on. So we do various levels of tests, I suppose you could call them. We have small unit tests for individual functions in the Gofer code, and we have larger integration tests. We call them end-to-end tests to verify sort of larger collections of functions. Those two types of tests are built into the code base itself, and every time the code is modified, so every time you release Gofer, all those tests have to run and they all have to give the expected answer. The reason for that is that when you're sort of working on some part of the code, it's quite easy to inadvertently break a different part, without thinking about it. So the having to run these tests every time ensures that if that does happen, the new code won't be merged and that breaking change won't be implemented. We also do a load of full-scale sort of engineering scale tests and benchmarking, where we compare to other software, both our own and other software by others that's available on the market. Here are some examples of those solver end-to-end tests. These happen to be from the Consolidation solver. So these are often sort of analytical problems where we know what the answer, they're solved problems, and we run them through Gofer, and of course it has to give the expected answer, otherwise something's gone wrong. We also do sort of simple comparisons to other software you can see on the right here. In terms of engineering scale, full scale problems, I mentioned we test against our own software. This is an example cross-check against Oasys Through. So it looks like a flexible retaining wall, cantilevered with a low behind and retaining a bit of water, maybe a sheet pile wall or something along those lines. And I've modeled the same situation in both Through and Gofer, and despite being fairly different calculation methods, we get a pretty good answer. So the graphs on the right are displacement of the wall, bending and shear force within the wall, and it's a pretty good match. Here is an equivalent check from Oasys Slope, looking at slope stability. So despite using completely different calculation methods, so Slope uses a limit equilibrium type approach. So the software effectively guesses at a large number of circular slips, calculates the factor of safety of each one, and gives you back the lowest. Gofer does almost the opposite. So Gofer doesn't guess any predetermined geometry. It just incrementally reduces the strength until the thing fails. And despite those very different calculation methods, we get very similar factors of safety, which is nice to see. Slope stability might be sort of one area where we, in some cases, might expect to get a slightly different factor of safety, particularly if the critical slip surface is very non-circular. Traditional limit equilibrium methods might struggle to give you the correct answer in those cases, but this particular test isn't really affected by that. So the critical slip is very circular, hence we get a similar factor of safety between the two different methods. I mentioned previously that we have plans to implement the limit equilibrium slope solver within Gofer, and that will be a really nice feature to have because we can do these different calculation methods on the same model with the same geometry, same soil parameters, and we can very quickly, do a limit equilibrium check and do a CFI check of a slope stability problem, for example. That'd be a nice feature to have. In terms of comparison to other software on the markets, I've got some slides comparing Gofer to Plaxis. This particular example is an embankment constructed on an undrained foundation, and then I allowed both models to consolidate. And we can see that we get a very similar match in terms of displacement contours, both magnitude and the distribution of the contours across the mesh. The graph at the top has picked out a couple of points, the crest of the embankment and the toe of the embankment, and I've plotted displacement versus time for those points. And again, we match up at the end, but we also match up along the shape of the curve, so that the consolidation is happening at the correct rate. So these two bits of software are using, I suppose, similar calculation methods, but they're obviously developed completely independently. So it's nice that we get a match there. And another example to Plaxis, this is a multi-stage propped undrained excavation with a consolidation stage, so maybe a sort of basement in London clay, something like that. Again, we get a good match for displacements, both magnitude and distribution of the displacement contours over the mesh. And on the right, we've got graphs of displacement of the wall, bending moment and shear force, the different colors, the different construction stages in the model. But for each one of those, we get a nice match between the two bits of software, as we should. So now a few words on the user API, again, because I've had quite a few people inquire about it, and we've heard how some engineers within Arup are starting to use it and starting to exploit it. So Gofer has an API, and what that means is that Gofer can be controlled programmatically or from another piece of compatible software. Typically, this is Python, so we can control Gofer from Python scripts, and we can do anything we like to it because the API has been integrated to Gofer from the start. Gofer models are just JSON files, they're just text files, and so it's very easy to modify them through code. And similarly, the results files that come back are also just text files, so it's easy to interrogate them, pull out data, create plots, and so on. Remember that Gofer isn't installed on the computer, so you can run the scripts from anywhere. Perhaps if there's a sort of a server hosting a model or a wider automation, that server, as long as it could authenticate with Gofer, could run the scripts and sort of update models and pull out updated results and so on. There are some really good examples of how to use the API within Gofer. There are some Jupyter notebooks that you can download and run, and they sort of clearly go through step by step how to use Python code to interact with an existing model and sort of make small changes, and it gradually builds up. We also have the Swagger UI, which shows the API commands and what the context for those and what you'd expect to get back from each of those. So it's really easy to start messing around and start having a play with. I'm going to show a few examples of how I use the API within Gofer. This one here is just to post-process results. So the model is, as you see on the left, some multi-stage propped sort of excavation. I've built the model entirely using the web browser, entirely using the graphical user interface, and I've run it and I've sort of made sure I'm happy with the results. But then I've used the user API to pull out those results and plot custom graphs. In this case, I wanted to plot multiple calculation stages on the same graph. So I've got my normal graphs of displacement and forces in the wall, but I've got different lines from different construction stages just to see how those change as the model progresses. Because it's all automated, if I make some changes, if I change my soil parameters in the model and rerun it, I can very quickly regenerate these graphs. So it's very quick and easy to do once you've set it up once. This is an example where I was playing around with a gravity retaining wall. I was looking at the impact of reducing the size of the wall base. So I've run various models, 7 or 8, I think, just playing around with the geometry of the wall, moving a couple of nodes within the model, remeshing, rerunning, and pulling out the new factor of safety of geotechnical failure on this wall. And of course, as the base width decreases, the factor of safety decreases. But it's a quick and easy way of working out the relationship between those two things, and how small can I make my base before the factor of safety becomes inadequate. This is another example where, again, I was playing with the gravity wall. I was looking at the sensitivity of the strength of the backfill material and also the strength of the foundation material. So the graph on the left is on X and Y. I'm varying those two parameters, and on the Z axis, I can see the displacement of the wall. And what it tells me is that, you know, both of those can vary a bit, but if both of them start to decrease a lot, then I've got problems because my wall starts to move a lot, and that's you know, going to cause me problems in terms of ground movements and so on. The other two graphs are just, I suppose, different ways of displaying that same information, looking at overall displacements of the wall based on the friction angle, and also horizontal displacements versus backfill friction angle. It's very easy to run this quantity of models. I think this was 200 or so different models that I ran through the API and just pulled the results out. Once you set up a small amount of code, it's very quick and efficient to go through this process. I'm very excited to see what an enthusiastic graduate with some Python knowledge can do if they get their hands on Gofer and start to go through this process and churn out large quantities of models. It's really, really exciting. So we're getting towards the end of today's webinar now. For those of you who may not know, we offer a 14-day trial of Gofer, a free trial. So if you go to the URL, which hopefully will appear in the chat at some point, you can register for that trial. It's registered per person rather than per company. So, you know, if you haven't previously registered, you can go and set up that trial and start having a play with Gofer. Build some models and see what you think of it. Lastly, we are also running a discovery survey, we're calling it, for Gofer. Again, there should be a link appearing in the chat soon, but there's just a few questions about how you may use Gofer or reasons why you don't use Gofer, and it would be very helpful if people go through and fill that out, just to give us some more information and help us improve the product going forward. So that's everything that we wanted to cover today. Thank you very much for joining and listening. I think we're gonna go over to the Q&A now, and we'll see what questions we have.
Okay, right. So yes, what we'll do now is I will look at the Q&A and we will go through, and I'll get the appropriate person to answer your questions. As I'm just waiting for those questions to load. Right, okay, so first question. if you have a plane strain, but it can also do an axial symmetry. Is that true or false?
So Gofer is unable to do axisymmetry presently. It's definitely something on the roadmap. You mentioned, shafts, tunneling shafts. That's an obvious use case for that. So the short answer is no, but it's certainly something that's on the roadmap.
Okay. Next question is, can a Gofer model sloping ground above or below retaining structures?
Another one for me, maybe. Yes, Gofer can. So we draw the geometry explicitly. So whatever configuration of slopes or other geometry there is in and around retained structures can be modeled explicitly. It moves away from the limiting assumptions on things like conventional gravity retaining walls, where you're messing around with beta angles and things like that.
Okay, and the next question is, does Gofer determine the time steps in consolidation analysis, or can you control that yourself? I think that's for you, Samila.
Yeah, so Gofer automatically calculates the time step. So the user doesn't need to include a time step, because the solver is written in a way such that it automatically computes the size of the time step, and end of each time step it checks the convergence criteria. So whatever you got for the answer is convergent and accurate for that specific time step. So towards the end of the analysis, Gofer automatically increase the time step. Sometimes it's to days or like in minutes, like you can increase the time steps to the course of the analysis, but it is happening automatically. The user doesn't need to compute like a minimum time step and add it. So it's full automatic.
Okay, the next question is to do with the different types of models available. So is there a schedule to add more soil constitutive, a more soil constitutive model, hardening soil model, or a small strain, a brick model, and more?
So this is very high on our roadmap. The initial work has been started on this. I agree, it's a very important thing to add. I'm just looking through, some sort of, as is suggested, general purpose hardening model is probably one of the early things that we are looking to adopt.
Okay. So look, now next question is, can Gofer model embedded retaining walls tied back to a gravity anchor or a second wall?
Yes. In the same way that I mentioned before, we can draw complex geometry explicitly. I'm struggling exactly to picture what's being described, but yes, sort of a double layer shoot pile wall or dead man type anchor. Yes, there's no reason why those sorts of solutions can't be modeled in Gofer.
Terrific. Okay, and right, I think is Gofer available via Unipack licenses, and if it's not, is it now available? So I think that is probably a question for me. Unipack licenses are available for all of our other softwares, and a Unipack license will be available in the near future also for Gofer. And that's Tony Swain. I'll come back to you a little bit later on and try and answer that one for you in due course. It's something that we're looking into, but it is something that we would like to offer soon. Next question. Given that the processing is on the cloud, removing PC hardware requirements from the user, is there a plan to add a 3D functionality?
I would love to add 3D functionality to Gofer. It's realistically quite a challenging task to do that.
Okay, so that's a nice to have that will possibly come one day, but obviously there's a couple of other things on the roadmap to come first. Okay, and can it also model geogrid or vertical drains?
So vertical drains can be modelled, again, explicitly with, I suppose, thin soil blocks with drain material to dissipate those excess pore pressures. Geogrid elements are another very high priority thing on the roadmap. So watch this space, they'll be coming soon.
Okay. Right, so it looks like we're actually out of questions for now. If there are any further questions, now's the time to put them forward. I'm just having a look. We can catch any if that were perhaps left in the chat. But no, for the time being, that seems to have been all the questions answered. If you do have any, speak now. Otherwise, if you would like to email oasys@arup.com, we will answer any further questions that you perhaps didn't think of today during the session. So with the Q&A over, I think that brings us to the end of our webinar for today. So we'd like to thank everybody for coming, and we'll see you at the next webinar.